Okay, so how many of you had a look on the lecture notes posted on the UTS online? Did anyone had a look for the UTS online lecture notes? Okay. So the first lecture is going to be about the characterizations of the bulk material, which is once again is going to be the most important thing, and you're going to use it in every design brochure you're going to have in the following weeks, except week 4. Okay, the week 4 actually was week 11 in the previous semester, but I just brought everything down because I wanted to give some space for the build conveyors, because usually we are going to have a catch-up session for that, and because one of the lecture we're going to miss on the 19th of April due to the Good Friday. So the solid handling and the processing we're going to talk about. First procedure is you have to have an identification key of the properties of the particle or the bulk crystallization material. Then you should have confident, accurate, and reliable optimal design and operation for your system. So without knowing the characteristic of the properties of your material, you cannot design your own system. Now, can you give me an example for that from what I talked about earlier and in the video we had from previous week? How will the characteristic of the material will decide what will be the system we're going to choose?
Know the state, like whether it is in an ash form or like in a solid form or liquid form.
Yeah. So in the case of the, well, we talk about the bulk. So actually the liquid itself is not going to be part of it. So we don't talk here about, for example, pumping the oil because it's just liquid. Okay, we can simply pump these things. But sometimes if you're going to work in a mine and you are going to have some, well, some soil due to the mining process. If you want to pump it out, you're either going to take it through the conveyors, but if the mine is going to be too narrow and too curvy, then it's much better to pump it up. And okay, so the characteristics and the classification of the materials, the method to be adopted and selection of the equipment for the material handling system primarily depends on the type of the materials to be handled. And therefore, it's going to be very important to know about the different types of the materials and their characteristics, which are going to be related to the method of the equipment used for their handling. And the basic classification of the material are in the basis of the forms, which are the gaseous, the liquid, the semi-liquids, and the solids. Solid from the majority of the material which are going to be handled in the industrial situation. And solids are classified in two main groups, which are the unit load and the bulk load or the bulk material. Now, what is the unit load? That's something I talked about in the introduction lecture. I have the sand, but I don't want simply to make a big system which is going to convey the things from one side to another. Simply by putting it in the bag, I can have a unit load, 30 kilogram of sand. I can carry it in the bag to another place. That's what we call the unit load. Or simply I can take it as a bulk load or the bulk material, which is the loose state, if it's going to be at a very high quantity. So the bulk materials are those which are going to be powdery, granules, or lumpy in the nature and are stored in heaps. So these are some of the examples of the bulk materials. An example of the bulk materials are the minerals, the earthy materials, the processed materials, the agricultural products, and similar other materials. And the major characteristics of the bulk materials so far, their handling is going to be concerned about is the lump size, the bulk weight, the specific weight, the moisture content, the flowability, the angles of repose, the abrasives, the temperature, the repo, pronesis to the explosion, the stickings, the fuming or dusty, corrosivity, and the hygroscopics. So most of these terms maybe you are familiar with, and the others we're going to clear it today. So these are some of the particle and the bulk properties. So for the particle properties, we care about the size, the shape, the surface area, the structure, the friability, the particle density, the hardness, the porosity, the strength, coefficient of restoration, the pickup velocity, the free settling velocity, the drag coefficient, the chemical composition, the hygroscopic capacity, the thermal sensitivity, toxicity, corrosiveness, the electrostatics, the combustionality, the color, radioactivity, and the magnetic sensitivity polarity. Well, if we're going to talk about the bulk properties, which are the main thing we're going to talk about, is the size distribution, the packing, the bulk density, the compressibility, the agglomerations, the moisture content, the internal strength, which is the because you're going to talk about the shear, the compressive and tensile today, the time consolidation, the cohesion, the wall fraction, the angle of repose, the fluidization, the diatration, the permeability, the convertibility, the buoyancy, the viscosity, the surface tension, the segregation, the dustability, the explosivity, and the voyage. So what do you know about these things? What are the terms you know from these terms? Let's go first for the size distribution.
Smallest to biggest?
Exactly. So actually what he said was correct. Now, if I'm going to have a material, it's going to have a different sizes. So I have to know where we're going to have the concentration of the big parts and the small parts. Now, if I'm going to have a mixture of gravel and sand, usually sand is going to go to the lower, the gravel will stay at the top. So that's what we talk about the sizes. The packing is, if I'm going to pack it, how much space I'm going to have between the particles, because it's very important. The bulk density, which is different from the actual density. The bulk density will be the actual size after we're going to have to compress it. So this is not going to include the spaces we're going to have in. So you know what the term density is, right? So it's the mass divided by the volume. Now, if I'm going to have the bulk density, that's what will be the actual mass on the actual volume I have. But the actual density is, I have to remove the spaces and consider this will be the new volume. That's usually the actual density is going to be higher than the bulk density. The compressibility is the ability to be compressed, and we have to care about this one, especially when we're designing the silos and bins. The moisture content, the internal strength, the time consolidation, the cohesion, we're going to go through this one in the next lecture. So first, this is the lump size. The lump size is going to be the longest length of the particle. We're not going to carry the shortest because this is the most important thing for us. So lump size of the material is determined by the distribution of the particle sizes. The largest diagonal size A of the particle in millimeter is called the particle size. The largest to the smallest size ratio of the particle of a lumpy material is above 2.5. They are considered to be unisized. So the average lump size of the size bulk material is going to be calculated by using this equation. Is going to be half of the A maximum plus A minimum. Simply is the average. So the bulk weight or the bulk density of the lumpy material is the weight of the material per unit volume in the bulk. So this is the bulky size. You can have space between them. So because of the empty spaces within the particle and the bulk materials, the bulk density is always less than the density of the particles of the same material. That's obvious because the volume is going to be bigger. Okay, so when you're going to, for example, the mass is going to be 100 kilogram. But first we put it with too many spaces in between. It's going to fill, for example, 1 cubic meter. So 100 divided by 1 cubic meter is going to give you the 1 kilogram per cubic meter. Sorry, 100 kilogram per cubic meter. But if I'm going to compress it, it's going to fill, for example, 0.8 of the volume. If I'm going to remove all the spaces, so definitely the actual density is going to be higher than the bulk density. Generally, the bulk load can be packed by a static or dynamic loading process. So once again, this is the bulk density. You can have spaces. When I'm going to do the compactation, I'm going to close all these spaces, and this will give me the actual density. The ratio of the bulk density of the backed material to its bulk density before packing is known as the packing coefficient, whose value is going to be varies from the different bulk materials and their lump size from the value of 1.05 to 1.5, and the bulk density is generally expressed in kilogram per cubic meter. We're just repeating something I know that you covered in our subject. Now, the angle of the repose is a very important term, and we are going to use it in the design process. Now, why we call it the angle of the repose? You can simply read that. Again, to put the material, the angle when it's going to stop, so it's pose. It was in pose and it's going to repose once again, and this is the angle of the repose. So the mobility, not flowability of the bulk material is generally determined by its angle of the repose. Now, what do you mean by that? Which material, if the angle of the repose is going to be lower, what does that mean? It's more mobile, right? And less mobility, that's the angle of the repose is going to be higher. So when the bulk material is going to be freely spilled over the horizontal plane, it's assumed it's have a conical heap, and the angle phi of the cone with the horizontal plane is called the angle of the repose. Less phi is higher the flowability is of the bulk material, and if the heap is going to be shaken, the heap becomes flatter, and the corresponding angle of the repose under the dynamic conditions is referred to be as the dynamic angle of repose, phi dynamic, where the phi dynamic is generally considered to be equal of 0.7 of the actual angle of the repose. Well, I didn't ask you about how do you want to divide the lecture time. Do you want to have 10 minutes every hour, or you want to have 2 hours, then 20 minutes, then we come back for the rest of the lecture? Or we can take it continuously and finish it earlier? So you can have a continuous sleeping in the class? Good. That's good. Okay, so we have codes for all the materials. And that's what we're going to learn later in the design process. So I can give you the code of the material and give you the tables. You know, this is an open book exam as any other exam we have at the UTS, but actually it was always an open book exam. So if you're going to have the code on the material, it's going to tell you something. So the first digit is going to be one of the alphabet A to G, specifying the lump size of the material. The second digit is going to be one number from 1 to 5, specifying the flowability of the material. The third digit is going to be a number from 6 to 9, specifying the abrasiveness. And the fourth one is going to be one alphabet from H to K, corresponding to the bulk density. And the last one is going to be one or more alphabets from L to Z, corresponding to the miscellaneous characteristics. So I know you know these things, but what is the abrasiveness is? You did manufacturing. Some of you did manufacturing with me. So we talked about the abrasive processing, which is something like how we can remove the material from the surface, but in the form of powder instead of, well, actually form of chips, but it's going to be very fine chips, which look like a powder. So the same thing, how this material is going to damage your material handling equipment by surface contact. So in this material code, if any of the above characteristics is not going to be known, the corresponding number or the alphabet is going to be drawn from the material code. So not all the material is going to have the 5 figures. Some of them is going to have 4 only. And the table below shows the description of the limits of the different classes of the material characteristics. As you can see here that, for example, the lump size, you are going to have, for example, dusty material like the cements. The A maximum is going to be up to 0.05 millimeters, and the class is going to be A. We said the classification for this one is going to be from A to G, right? So this is how it's going to be classified from A to G. So the A is going to be for the dusty material, but the G is going to be if the A max is going to be more than 500 millimeters. So how much 500 millimeter? How many centimeters? It's half meter, right? 50 centimeters. So if I'm going to have a big rock, we can put the G. If we're going to have dusty material, we can put A. Something in the middle, if we're going to have a small sized lumpy like the iron ore, where the A is going to be something between 10, which is 1 centimeters, up to 60 millimeters, we can put the D. And everything is going to be above or below, depending on the A value. For the flowability, that's the second one. We said it's going to be a number from 1 to 5. So how can we simply classify the 1 to 5? Is going to be about the angle of repose for this material. If the angle of the repose is something between 0 and 20, which is going to be very free-falling material, like the cement, when I'm going to put it on the table, it's going to get flattened rather than it's going to get the cone shape. I'm going to put the number 1. But if it's going to be a sluggish, like the wood chips, the baggers, or the foundry sands, the angle of the repose is going to be more than 40, and then I'm going to put the figure 5. In the middle, number 3 is going to be for the average flowing, where the angle of the repose something between 30 to 35. Now, the third digit is going to be for the abrasiveness, and this will be once again a number from 6 to 9. Now, if the material is going to be non-abrasive, like the grain, it just follow without doing any scratch on your system, I will give it 6. But if I'm going to have very sharp material, which is going to make scratch to the system, we can simply put the number 9. And for the abrasive, like the alumina, we are going to put number 7. For the bulk density, depend on the density itself and how much, what will be the alphabet number we're going to put. So it's H to K. H, if it's going to be very light, low bulk density, up to 0.6 ton per cubic meter, or very, very heavy, very high bulk density from 2 to 4 ton per cubic meter, I'll put the term K. And the I and the J is going to be for the medium and the heavy bulk density. The last one is the miscellaneous characteristics, and this will depend simply on the aeratus and the flow fluid, the contained explosive, the sticky, the contaminable, the draggables, the harmful fumes or dust, the highly corrosive, the mildly corrosive, the hygroscopic, and so on. So sometimes you cannot find these things. So sometimes the code is only going to be 4 figures instead of 5 figures if we are not going to add this the fifth digit, which is the miscellaneous characteristics. This only going to be additive if it does have, I have something. Anyone computer did that? Yeah, because I'm worried about cutting the recording from time to time. I have to check the computer. Okay, so going for the actual material properties chart. Sorry?
Can I ask something? If you go back one, what about if something has two of these characteristics? Materials have two.
You mean it's going to have an explosive or the sticky at the same time?
Yeah.
That's a good question. I never asked that before.
We did have the 2 letters next to each other.
I never seen anyone have 2 letters beside
okay.
that. Okay? Usually it's maximum 5,
Okay.
minimum 4.
Okay.
But I'm going to answer this question anyway. I will come back to you next week with an answer. Send me an email to remind me.
Yeah. Okay.
You can?
In the slide before, it says you can. Like a couple before.
Yeah, I'm going to. Okay.
on Longham, yeah. When you were talking about,
Yeah, we're talking here, right?
yeah.
It's not known. Wait a second. One or yeah, more yeah, one or more alphabets will be here. Yes, that's good. I'll give you an extra mark for that. Oh, sorry, I'm blocking your way.
That's okay.
I'm blocking your way and show that.
Yeah.
That's very smart.
You were over there before.
Oh, yeah. Okay, so sorry, this is the table of the material properties, and you are going to go through this one multiple times when you are going to do design, especially when we start for the screw conveyor, the bulk of the pocket elevators, and the flat belt design. So, for example, we're going to take one of the examples here is the ammonium chloride. So you can see that this is the density, and this is the surcharge angle, the angle of the repose, the maximum conveyor slope, the abrasiveness, and the corrosiveness. So away from the unknown codes, take the mass of the ammonium chloride, the angle of the repose, and let's start to at least find the 2 digits we have to put in the material code. So let's write down here that the density is something about 832 kilogram per cubic meter, or the 0.8 ton per cubic meter. The angle of the repose here is something between 30 to 44 degree.
It's a very big range, no?
Yeah.
Because we have
Depend on what?
If you want to write the material code,
Yeah.
you're gonna have to which one will choose?
Well, that's depend on what. Now, why we have the angle of the repose is varying from 30 to 44. So we have something at 14 degree. That's why we have this difference. Now, think about it.
It depends on the density of the material.
Nope, not the density.
Size of the grain.
Nope.
How much we pouring the material or something.
It's about the moisture content. Okay, so if you have the same, you have two bags. One of them was opened in a humid day. The other one was sealed. Then you are going to bring both and try to check what will be the angle of the repose. So the open bag will going to have very high angle of repose. The other one is going to go flatten.
So it's all about humidity.
Moisture content. Okay, so we are going to check about that, and actually it's going to be a very important factor also in the design. What else we have is yeah, well, usually the moisture content is going to be increased at the as long as we are going to store it, and that's what we're going to see in the experimental procedure in week 3. Okay, so we took 330 to 44, and let's try to check about the first the class we are going to have for the lump size. Sorry, we're talking about the bulk density. So yeah, so we got between 0.6 to 1.6, so it's going to be the I. And the angle of the repose was something between 30 to 44. So either 3 or 4, you go to the maximum, which is 4.
4 or 5 because it's 44.
Yeah, but it's most of the value is going to be within this range.
Oh,
Yeah,
so we choose the average.
based on the average. Yeah. If you're going to have, for example, how to design a system for a certain material, and you found that the range is going to be varying too much, usually you're going to the minimum. That's in the class. But in the real life, you have to take samples and check which one is going to be according to the time, and then you have to take the maximum. Because if you are going to have, for example, a storage, you have to empty it from time to time. You don't know when the people are going to take your merchandise, when you're going to empty these things. But usually they're putting a limited time. So for the silo, for example, they have a timetable. They have to empty it from time to time. Otherwise, the things will be built up, and it's going to be very hard to empty the silo. And that's what we're going to see next in the flowability analysis. Okay, so the bulk materials are generally handled by a belt conveyors, screw conveyor, pneumatic conveyor, pocket elevator, grab pocket, skip hoist, stacker reclaimer, the dumbbell loader, or extra. depend on what? On the characteristic we're going to have for this material. This can be handled by cranes, trucks, when it's going to be collected in container or bags. That's mean we're going to have a unit load. The small lumps, like the powder granules, materials can be simply handled by pneumatically or hydraulically. Pneumatically, that's mean we're going to use the mix the material with the air and send it through the pipes, and then we can separate them later. Or simply we can mix the thing with the water, pump it to the other side, and we can separately by the spinning process. The bulk materials are generally stored in the ground or floor, in the open or under shed, or simply can be done in bunkers and silos, depend on the materials and how they can take the effects of the environment. Everything actually was described in the previous lecture. Now about the size control. How can we control the size of the material? Yeah, the problem, I cannot play the video now because I have technical problem with this one, but simply we can do the vibrating grizzly. It's something, you can see that the first one is going to be bigger than this, bigger than the second one and third one and so on. So the shaking of the things, we're only going to have the big parts going to be stay, it's going to go from one level to another, but all the sand is going to go down. Simply we can have the shredder, which cutting the parts of the material to a smaller size, depending on the distance between the shredder edges. I can play with you for this one. This is a gravity crusher. I think we covered this one earlier, but I don't remember when. Okay, so it's just simply going to smash the bulky size to a smaller size. The rotary screen, same procedure. Okay, so it's breaking the things until we're going to have a smaller size. Usually this one is then done by stages. Actually, all the operation is done by stages. You cannot do it from the very big size to the powder. You have to do it in multiple stages until you are going to have the desired size. This is vibrating screen, which is very popular in the mining, especially in the gold mining procedure. I think this video should be played soon. Yeah. By the way, this is the belt conveyor we use in the mining. I don't want to show you the sound because I have to turn off the mic, and in this case, it's going to be very hard to redefine once again. Okay, so as you can see here, that's what will happen. The vibrating screen. The smaller part will fall inside these small holes, and the bigger part will come to the end. So we're simply separating the small and the bigger parts, and we can have it once again into multi-stages. So we can divide it into 10 sizes, for example.
And can we change the other one? So smaller holes or
Yeah, the smaller is going down there. The bigger will go to the other side. It's just separating in process. They don't mix together, by the way. It's going to have two different openings. Okay, so these are the common methods of the size analysis depending on the size we're going to have for the particle itself. If the approximate size range is going to be something between 125 millimeters to 38 micrometers, simply I can use the mechanical sieving process. The sedimentation process, if we're going to have smaller size, something between 100 micrometers to 2 micrometers, the microscope, if it's going to be too small, up to 1 micrometers, the electron microscopes, the scanning electron microscopes, the classification, and the laser diffraction. So this is procedure actually you are going to do in the lab. You are going to use the mechanical sieving process. Yes?
Sir, actually recently you told that the envelope repose,
Yeah.
which is the study on the ground of any kind of soils or any kind of materials. But sometimes we look at many kinds of soils solids and materials which help of standing with the retaining wall. So is there any changes in the angle of repose?
Once again, it's about the moisture content you are going to have in the sand. There's going to be dry sand, the angle of repose is going to be too small. There's going to be wet, the angle of repose is going to be too high, right?
So sometimes the sand is standing on the ground with the help by the retaining wall.
That's different. That's different. The angle of repose measurement, it doesn't have to have any support. You just simply bring the sand, you put it on the flat surface, you stop, it's going to repose, and you measure this angle. You don't have to support it with anything. That's a different issue. Okay. So as we're going to have a smaller size range, you have to use a more complicated procedure to determine what will be the size of the parts you are going to have. So based on the experience, if you're going to have the dry sieving measurements, the minimum 90 to 106 micrometer you are going to get. For the wet sieving, you are going to have minimum 75 micrometers. And for the laser deflection, the maximum is going to be 500 micromillimeters. So the first procedure is going to be the sieving. I'm going to describe that, and we're going to give you some example for the experiment you're going to have in week 3. Week 3 experiment is going to be in lab at B4. You went to B4 before, building 11, B4? I'll show you the way. Maybe tonight, maybe later. Anyway, we are going to have two tutors from the civil engineering, and I have to divide the class into 6 groups. So what's happened is that in the first hour, 6 to 7, 2 groups are going to work in parallel. Group 1 is going to do experiment number 1, group 2 experiment number 2. Then after 6:30, you are going to flip, and then 3 and 4 in 7 to 8, and the last hour is going to be for the group 5 and 6. So did I post the groups yet? No. Okay, now you have to work in the groups, but actually the report is going to be individual. That means you can work together on the group, but I would like to have the discussion of each report is going to be personal. It's not going to be a work group. Now, why I'm doing that? Because this is very important. The design for this subject is very important. Actually, it's in any other subject. I don't believe that the design process for one part can be a group work. Why? I don't believe that writing a report, helping the others by writing the report, is a contribution in the work. Because when you're going to go for the real life, you cannot tell your boss that, okay, well, I did this experiment with my friends, but I was the person who wrote the report, so I don't know what's the actual thing happening. So I encourage everyone to do the calculation by himself and try to actually contribute in the lab. So you will see the experiment, you will understand what's going on, because you are going to have a pre-knowledge about that now. So this is the sieving process. That's an old one. Actually, what those people doing is just simply separate the small parts, keeping the big parts at the top. But that's what we are going to do in the lab. That's what we call the mechanical sieve shaker. The coarse sieve is going to be at the top, and the finest one is going to be at the bottom, and we can have the pan at the bottom. So I'm going to put the material at the top. Start to do shaking process. The bigger particle is going to stay there by a certain percentage. Then the next one is going to keep the little bit smaller until we're going to finish maybe with nothing at the pan. Maybe the finest material will stuck in the second last or the last sieve without going at the end. So what's the principle of that? We should know what the size of each sieve. How can we simply define what the size of the sieve is? The hole between it, okay? Or the density. It's either. Now, the lower density, that means it's going to have a bigger size. The smaller density is going to have the smaller size, or we can simply say that this sieve can pass the particle of 5 micromillimeters. So a percentage of the material is going to held by each sieve. For example, it's going to be 10 levels. This one is going to carry 5%. This one is going to carry 50%, 20%, until we're going to have the adding up of everything is going to be 100%. It's not going to be about the volume, it's going to be about the mass. How much mass did this one hold? How much mass does this one hold? When you are going to add them all, should be 100%. So you can tell about the percentage, what the size of the material particles, and you can sketch a diagram, and you can find something from that. So these are the different types of the sieves. You can have either the perforated plates with the circle holes, the square holes, and we can have the woven mesh. Okay, so this is the standards for the mesh size for different sieves. You don't have to read all that. You're going to use it actually in the lab. The guys there will tell you how to use them. You can either do the ISO standard, the DIN, the German, the US, Taylor, which is American as well, and the British standard. Well, usually we're using the ISO standard. Now, this is work example for the sieve from previous semester. Well, actually, it was 2 years ago. I tried to impose this one for last semester as a lab experiment, but then we decided to have a video lab between us and Wollongong University. But as I told you, this semester, everything is set up. We are going to do the experiment at level B4, building 11. So what's that? Is the size of the sieve we are going to have. The chorus is going to be at the top. The size is 1,800 micrometers. The smaller one is 300 micromillimeters. That means everything is going to pass the 300 is going to be considered 200. Everything will remain in the pan is going to be less than 200, which is 300, which is going to be the 200 one. So we put the material at the top. We start to do the shaking. What's happened is that nothing has been installed by the bigger sieve. 6 grams held by the second, 30.32, 39.41, 20.71, 12.34, 7.91, and 1.76. And what dropped to the pan was 0.65. We weigh how much has been held by each sieve. I can simply make it as a percentage. How? If I'm going to add up everything here is 119.1. So the 6 divided by 109.5 is going to be 5.04%. And I finish the other row of the column of the table. This is the percentage of the mass retained, 5%. This one is 30.5, which is the 5.04 plus 25.46. And I'm going to add everything. I'm going to have at the end 100%. The mass passing from this one is 100%. Everything passed the first one, and only 0.55% passed the last one. Of course, nothing passed the pan because the pan is not doesn't have a holes. So we have these values, and we start to do some graphs to get what we want to. The first graph is going to be about the mass percentage more than the diameter we are going to have in this side, and we are going to have the particle size depending on the sieve size we are going to have. So the maximum sieve size was 1,800 micrometers. How much held? 0%. For the next one, which was the 1,400, the 5.04%. Okay, that's the point. Then we continue doing all the points and make the first curve, which is the cumulative retained distribution of the material. The next diagram is the cumulative passing distribution, the other way, how much passed, not the how much held. So once again, the particle size for the smallest sieve, which was 200, because we said that everything left in the pan was less than 300, so we considered at least 200. So that's 200 the percentage was 0.55%. Okay, and we start to do the diagram on the other side. Now we have a cumulative passing and the cumulative retained, put both on the same graph, and we're going to have the intersection between them. Okay, so here we are going to have the average diameter for the material we have been tested. That's what you're going to do in the lab. Okay, so for the cumulative distribution, the cumulative passing was the undersized, and the cumulative retained was the oversized. So the median particle diameter for the data we have been analyzed was equal to 0.7 millimeters, which is 700 micrometers. We always call the median particle diameters as D50. We are going to use this term multiple times in this course. Okay, now for the frequency distribution, we don't want to consider this one because actually nothing was held in this side. So we can start from the 1400, and we're going to have the calculation for the average sieve size of the 1600 micrometers. We can simply make another diagram. We don't use the 1800 because it was zero, nothing was held there. And this is the 300 and the 1600. And we're going to use the mass percentage on each one to make the frequency distribution for the material on the sieve. We can make the frequency distribution by the same process. This is at diameters, and we can use the percent of the retained on the sieve, but we can use the histogram to sketch the frequency distribution chart. But I think this will be fair enough. Now, if the size is much smaller, we cannot use the sieve, for example, for the powder. So we go for more advanced procedure. We list many technologies here. Okay, but we're going to talk about the laser diffraction. Now, I covered laser diffraction before because I used to have a demo for this student at Wollongong University. But once again, I can bring you a video for that, which is going to describe to you how the process is happening. I'm going to post it for you on UTS Online. And actually, I didn't check with the civil engineer if they do have this machine or not. So laser diffraction measures the particle size distribution by simply measuring the angular variations and the intensity of the light scattered as the laser beam passes through the dispersed particle sample. And the large particles scatter light at the small angles relative to the laser beam, and the small particles scatter light at the large angles, as illustrated as below. So it's simply just sending the light. We're going to have a reflection from the material, depending on the size of the particle we're going to have. The smaller size, that means a smaller part. The bigger scatter, that means it's going to be a bigger part. This is a machine. I can send, as I told you, I can send you a video for the master sizes machine and how it's works. So this one is give you a full report. You don't have to do the measurement by yourself. You don't have to do all these graphs on Excel sheet and get the equation and get the values. To give you a full report. And as I told you once again, this is very popular in the pharmaceutical industry because they're dealing with powder. Let's even give you the graphs for the volume and the particle size as a percentage. And these are the equation for the particle diameters used by the device. But still, we can use this one. For example, the ds, which is diameter of the sphere having the same surface area as the particles. The ds is going to be equal to the surface area divided by pi up to power half. And for the dv, which is the diameter of the sphere having the same volume as the particle, it's going to be 6 multiplied by the volume divided by pi up to under square root of cubic root of 3. And the dA is diameter of the sphere having the same projected area as the particle. We are going to have the this equation dCF, dF, and the dm. So for the particle, we can have further diameter, which is going to be the Ferret's diameters and the Martin diameters. Now, two theories. Ferret says, okay, now I'm going to take the largest diameter, whatever the shape of the particle is. For the Martin, the length of the chord through the centroid that divided the projected area of the particle into two equal parts is going to be the diameter he's going to use. So two different theories, but at the end the difference is not going to be that much, because actually both has been used in the crystallization of the material and when they do the tables. Okay, so this is the more complicated description of the particle, because even the particle of the sand is not going to be just spherical shape. Usually it's going to be a lumpy shape, and this is the method on how to take the diameters of fritter or the other type. Okay, so this is distribution of the particle size and the mass under size, and how we can sketch the diagram accordingly for different product, of course, as you can see here. Now, one of the tests we can do for the material is we said the bulk density and the compressibility of the material. What will be the use of the compressibility?
How compact you can make it and transfer it.
So you can fill the same pin with more material. But this is not always a good thing. And that's what you're going to see next.
Some material will break.
Yeah, and they're going to be held inside, so it's going to be harder to take it out.
Yeah.
So for the bulk density rho, or rho B, we're going to do the compressibility test. So at the initial stress, when we're going to have zero stress on the material, this will be the density 1. The density 2, when we are going to add some stress on it to compress it to a certain level. And the sigma C is the maximum stress we can put for the material, so it's not going to compress further. So we're going to have 3 stresses, and we are going to have 3 densities. What's happening? Why we have 3 densities? Yeah, because we have 3 different volumes. But what is the constant? The mass is constant. So simply we are going to have 3 different densities in this case. So simply sketch that. Now why the A is standing on the y-axis? Because its stress was 0. Is it free? We just filled the pocket to the top. We didn't add any stress on it. Then we start to compress it to a certain level. Compress it till the end. Now it's not going to move further. This will be C. So we can sketch that. We can, more points is going to be more accurate measurements. Oh, it's not reaching that. Okay, so that's the device which can do that. And I hope that we are going to do this one, because I forgot which experiment they told me about. But they told me about the Jenkins shear test one. But anyway, I think this can be a good project for the capstone. If one of the students would like to build one for us. Anyone here happy to do that?
Which project?
Capstone?
Yeah.
Next semester.
Next semester.
Yes.
As in Ashburn.
So we are going to have someone to build that for us. You can come back in 1 year.
1 year.
1 year to run the test.
Drop the course and come back. What is the unit of measure?
Which one? Actually, you put load here. Okay, you hang the load from this side.
Yeah.
Okay, and what you are going to have a Newton,
Yes.
and you know the area.
Yes.
You divide the Newton by the area.
Newton's gonna get stressed. Yep.
Exactly.
That's it.
That's it.
That's all. Oh, so compressibility is measured.
Yes.
In megapascals.
Yes.
Yeah.
Now, what do you need next? The density. So, for example, I'm going to start this experiment by filling the sample of 1 kilogram. I know what the volume, initial volume is. I didn't add any load. I just filled to the top, 1 kilogram. By the initial volume, I will get the density number 1, no load at this stage. Then, for example, I'm going to add load on these sides, actually, and it's going to compress it further. I can measure how much it went down, because we have measurements on this side. The H, you can see the H. When it stopped, I got the new volume. Divide the mass by the new volume, I'll get the density 2. I know what the load is in Newton. I know what the area is. I will measure the sigma, the stress. Then I will keep doing that until I put the maximum load and the H didn't change. So this is the sigma C, and this is my final density, and I'm going to make this sketch. So you can see here for this, for example, for this device, the base diameter is equal to 63.5 millimeters, and the internal height at the beginning, without adding any load, was 19 millimeter. So these are the basic things, and as whenever I'm going to add something, the stress will increase and the height will decrease. So I'm going to end up by having this diagram. This is the major consolidation in kilopascal, and this is the bulk density in kilogram per cubic meter. Put the points, use the Excel sheet to generate the line for you, and you can get the equation for it. Okay, knowing what the actual stress was, the initial was 5.939 kilopascal. Then you can know what will be the actual density, the bulk density of the material you're doing the measurements for. I will give you I will send you some data today, and this will be a good experience, practice for you. Yeah, I'm going to send you the data. You have this recording. You have the on UTS Online. I'll give you data. You start to do the sketching of this major consolidation stress against the bulk density, generate the curve, and get the equation. Because actually you're going to use something similar in the assignment number 1, something we're going to discuss today. So the bulk density is the most important parameters that affect the bulk material handling, the BMH, operation basis on the pricing. Also, the most difficult and frustrating parameter to get. The reason is that the bulk material usually is going to be variable. It's not going to be constant. The exaggerated by the numbers of the definition, like the loose poured, the tapped or compacted, the vibrated, the fluidized, and is going to be actually the operator dependent procedure. Also extrapolated by the various measurements techniques and the standards like the ISO, the AS, the BS extra, and also for different products. Proper definition and characterization process, essential, understanding, which is the equally important. And Trotter actually from Mulligan University, you can refer to this reference to read about the procedure he used to do the measurements for the bulk density. I'll try to send you a link for him because I'm not sure if you have an access for the copyrighted materials. So once again, this is the bulk density. We have 200-liter drum. We have gently poured in wheat. The mass of the solid basically was 160 kilogram. The loose poured bulk density was 160 divided by the volume, which is going to be 800 kilogram per cubic meter. From the other test we had, the apparent density of the wheat particles was 1,400 kilogram per cubic meter. But here we got 800 kilogram per cubic meter. The salt volume is going to be equal to 160 we got for the mass divided by 1,450 kilogram. So it's supposed to be 0.11 cubic meter. Okay, now this is the salt volume of the material we have. So what the rest is the air. Okay, so the air volume is 200, which is total volume of the drum minus the solid volume we got. And this will give you 90 liters of air volume is between the particles of the wheat we have in this barrel. So the difference voyage, lambda, is going to be equal to 1 minus the rho B divided by the rho S. So this one, 800, divided by the 1,450, and this will give you 0.45.
So
yes.
We can compress now up to 0.45?
You didn't compress anything.
No, I mean after that. So you know now the void, how much void you have. So now you can compress up to 0.6.
Don't compress because you may crash it. You don't want to crash it.
If it's compressed. Oh, right.
Yeah. Okay. This will be important in which case? In the storing and in the shipping. if you want to put in a ship, you will know exactly what the volume you would like to have to and how much you are going to add in. So these are some of the tests we can do for the particle density procedure by having two pistons, which are going to do the measurements by compressing and tell you exactly what the air volume is going to go to the other side. This can be done by the measurements or simply by the calculations. Okay, so usually it's not good for the mixture of particles having different rho value. I thought my ear is too big to hold the thing, but also the specific gravity bottle, which is the relative density or the water displacement method, can be used. Okay, now from this experiment, let's have a question. Actually, in the previous semester, we had another assignment number 1, which is 5% theoretically, and it's depend on the thinking, which is the common sense. Now, just consider yourself, you're living in the, let's say, the 16th century, and you would like to fill a boat with wheat, and you don't have any method to weighing how much you are going to give them. So what would be the method to know how much wheat you did put in this boat?
Take one measurement as sample and do like this every time.
Nope.
Take the volume of the ship.
There's something right here. Now we're talking about displacement method, okay? Yeah, that's why most of the ship in the till actually it's happened in Iraq 2003 because when they tried to sell the oil, all the counters didn't work. So actually they were checking the displacement of the water for the ship. Okay. The volume of the water, the density of the water is known, so they know what the mass of the oil has been shipped, and they can check what actually the amount of the oil has been put on this ship. Okay, so yeah, exactly. Okay, so this was a question, and some students couldn't thought about it last semester, so that's why I removed the question. Do you want to have it in the final exam? I just give you the answer. I just give you the answer. That's cheating.
You said for me.
No, I just kidding. No, actually, the good thing that last year nobody did the alternative exam. That's mean the alternative exam for the past year is going to be the main exam for this semester. The thing is, okay, now just let me remind you about something. All the assessment we are going to have is going to depend on your student number, i.e. the last 2 digits of your student number, the first and the second from the right, is going to be P and the Q. That means the parameter of the design for most of the question will depend on these 2 figures. Something is going to be added or subtract or whatever the thing is. So everyone have to work on his own solution. But that doesn't mean that you're going to sit together doing the solution. Okay, because you have the right to share the procedure of the solution, but you don't have the right to share the solution itself. For the hydraulic conveying, I will try to give you some time. In week, actually going to week number 8 with the sequence, we will sit in the class and we're going to do the solution here. Okay, that means you're going to have the time to ask me. I'll give you some help. You finalize everything. Maybe it's going to take 1 hour. Then you go scan it and upload everything online. Okay. Basically, I'm not going to be the marker. I don't have time to do the marking. So I hired 3 markers. We have good, bad, I won't say ugly, and better, actually. So one of the marker is too harsh. So the problem is that it's going to be a random distribution. You don't know who the marker is. So well, she or he, they are restricted because they don't like the copying. So that's why you have to avoid the copying. Okay. Uh, Once again, work together, but try to make a different solution. Even write down with your own style. Don't copy other person's style. You don't know if he's right or good. Another lesson is this subject is not double pass. That means you only have to get 50% you will pass. But that doesn't mean that you have to make less of the final exam. Because what will be the reason for not getting C or D in this subject? Right? So just keep doing the good work till the last minute. Okay, so this is some terminology for the characteristic particle shape we have. For example, for the acicular shape, the description of the particle is going to be a needle shape. You can have parts which have a needle shape. The angular with the sharp edges or having roughly polyhedral shape. The crystalline shape of the geometric shape freely developed in the fluid medium. We have, for example, I don't have to go through everything. The flaky, we have the granules, the irregular shape, the nodular shape, and the spherical shape. The spherical shape usually considered to be the best because have the higher flowability, and that means it's going to be stored and empty in very easy way. Yeah, it's compatible, yeah, but easy to flow. It even can be free flow. You don't have to use any equipment to do that. Okay, so the particle shape will affect the flowability, the packing, and the apparition. So that's why the spherical actually is going to be good flowable and less apparition. And that's why it's the best geometry you can have for the particle. The particle morphology quantitative study of the particle shape. For the sphericity, the lambda is going to be, sorry, the epsilon is equal to the dsv divided by the dv. We talked about these diameters before here. The different diameters we can have. Okay, that's dv, dA, and so on. So how we can use actually these diameters with diameter of the sphere the same surface as the particle, diameter of the sphere having the same volume of the particles, diameter of the sphere having the same projected area as the particle, and diameter of the sphere having the same surface area to volume as the particle. And the Ferret and the Martins diameters we use next. Okay, so that means it's going to have the same volume, surface volume divided by the diameter of the particle which had the same is going to be equal to the psi. So in the case of the material, the value of the psi is going to be equal to 0.5, which is going to be angular, and this will be for the polarized cool, while in the similar is going to be equal to 0.59. For the fly ash, of the psi is going to be equal to 90, which is going to be an approximated sphere shape. So use frequency to define the shape of the particles we are going to have for different materials under material handling. For the Mohs scale of the hardness for the material, the Mohs scale hardness from 1 to 10. And this also involves of the sum of the material codes in different standards. So 1 is going to be very fine, very soft, like the powder between fingers, like the talc material. And the 10 is going to be for the diamonds, going to be very rough. You can see that everything above 7 is going to be for the quartz, the topaz, the rhodium, which is going to be very hard material. While the fine material like the talc, the gypsum is going to take 2. The calcite is going to be 3, which can be scratched the fingernail when you do the test for it. Well, we said something about put it on silent, right? Who's that? Who used the old system for them?
Yeah.
Update your.
So that's a scale of hardness.
The hardness.
Yeah,
You know what the hardness is, right? Yeah.
But I've just seen so many other tests and like scales before
Yeah.
in terms of like indentation and stuff.
Oh, you're talking about the hardness test.
Yeah.
That's different.
Okay.
Okay. Now this is for the particles.
Oh,
Okay, this scales for the particles, and know the hardness test when you get the Brill. I forgot the name. Brill hardness test and the other. Yeah, that's different one.
okay. But
Okay.
after you test materials for hardness, you need to classify them or something or no?
Yeah, it's going to be useful when you get because for the abrasivity of the material.
Oh, all right.
Yes, the harder material is going to be more abrasive,
Okay.
and we can see more application about that. Okay, so this is the Brunel scales. This is the original Morse circle, depending on that. Okay, so you can see that we are going to talk about 1 to 10 instead of the 1 to 2000 we have in the Brunel test. The flow properties of the bulk material is very important, and you will notice about that when you're going to do the design of the silo in the assignment number 1. Now, what the example we can have for an everyday flowability test? Well, it's happened sometime when, for example, you have some powder stored in any can, and after a few days or a few months, you try to empty the things, there will be something built up in the middle, right? Like the coffee, yes. So we will see what will be the other type we're going to have in the case of the silo. And actually this is very important because sometimes you spend sometimes a long time to do a design for something, manufacturing something, but because you miss something about the flowability of the bulk material, you will end up to take down your own product. And we will see, for example, here, what will be the types of the flow properties we are going to have. So the flow properties actually is a mechanical property and used to compare and optimize the bulk material regarding flowability and design the bulk material handling equipment like the silo, the feeders, the flow promoting devices, and other bulk solid handling equipment. We are going to have to check what will be the flow properties for the material. Okay, done. Okay, so for the bulk material handling plant, what we should know about the products we are going to design the material for. First, an area where there's frequently a lack of the attention in the design process, which is the handling process. The characteristics of the flow properties of the bulk materials. We have to know what the major bulk material plants still being built without any good information about the flow property, and hence we're going to check about the flowability and the hardenability. The specification provide the scanned information like the mean particle size and the bulk density and so on. So what are the flow properties? That's what you're going to design actually. You have a question about that, and we're going to learn about the design procedure in next week. To design the pins and associated handling system for the bulk solid, it's essential to access to relevant flow properties like what are the bulk density, what the kinetic angle of the internal fraction phi, what the static angle of the internal fraction phi t, what the effective angle of the internal fraction delta, what the wall fraction phi w, what the flow fraction, or what you know as the FF for the which is going to represent the internal strength of the material, the cohesion and the adhesion, and the time constellations according to the temperature, the size, and extra. So why we have to measure the flow properties? First, for the qualitative application, which is the flowability testing. Will the powder will flow in existing equipment? Will it flow uniformly? Will it going to be accept caking after long-term storage? And that's actually what's happening to the coffee inside the jar. It's having cooking, yes, okay? So it's became something like a cake. And can flowability be improved by adding flow agents, the particle size distribution, control the moisture, the surface characteristics, or according to the temperature. Are flowability specification met for the quality control purposes? Also, for the quantitative applications, for the equipment design itself, the goal is to avoid the flow problem with the equipment by appropriate design according to flow properties. Okay, so most of the storage and the processing system for the powders are based on the gravity flow. You can add some equipment to increase the flowability, but usually we would like to open the flipper and go to flow directly. You don't have to add anything. Most of flow problems appear while discharging of the hoopers, containers, hips, and soils. It's not with the filling the things because it's the easiest way. To understand these flow problems, it's important to know how the powder is going to flow. Now, these are the problems we are going to have. That's what we would like to have for the flow pattern. We would like it to flow at the same speed in all the points we have inside the silo toward the exit. But actually, that's what will happen. We are going to have some stagnant zones on the side. It's going to be a built-up one due to the caking mostly, or the bad design, or even for the angle or the surface roughness. And thus we are going to have the material flowing from the middle, or have some built up on the sides, and we are going to have a definition for that later. So that's what we would like to have, a mass flow. We're always looking for the massive flow, where the entire contents is going to flowing downwards at the same time. But to achieve the massive flow, the hooper walls must be sufficiently smooth and steep. If you are going to make this angle, okay, less steeper, of course the material is going to be built up on this side. So more steep, better flowability. Okay, this is the funnel flow we can have. It's going to have funnel size, where we're going to have stagnant zones prevail on the hooper walls. Stagnant zones may be non-symmetrical. It doesn't have to be exactly like that. And sometimes the funnel flow cannot be identified from the top of the silo. So you go to the top, you look at, and you cannot see that the thing's happening actually. Unless if you're going to have one of the cases which call it the rat hole, where you're going to have a small hole in the middle, that the material has been emptied only in this column, but anything on the side was simply stagnant. So these are the flow properties needed to avoid the flow obstructions, like having the bridging process. Now what's happening is that this material has been built up, but what we have the arc built up, preventing the whole material from flowing down. Or we can have what we call the rat holing. So just the material in the middle has been void, but we are going to have the stable annular region on the side. Now, what's the, well, we are going to have further, but if we are going to have these two cases, what's your suggestion to make the things flow? Have you studied earlier? Have you done this subject before? Anyway, but actually he's giving smart answers. But anyway, what happened in the real life, that they're not going to inform the engineer about that. So what's happening is that the worker, they are going to bring a hammer and start to knock on the silo, damaging the wall. But actually, it's make the thing work temporary. But the best thing to do that is sometimes they put in vibrations inside the thing, make the shaking, making everything flowing down. You can, well, actually, there's no, you don't have to do it manually. Sometimes instead of using the vibration, they're blowing the air, okay, in rings all over the thing and make the things flowing down. There's mixer. I will show you some example for that in a video lecture I will send. Okay, because I did for last semester. We don't have time to do it this semester. So I will post the same video and you can see what are the answers for this problem. So This is the massive flow. We said that all the velocity of the material is going to be all the same in all the in motion along all the walls. We have to know about the diameter. We have to know typically the height is going to be 0.7 multiplied by diameter to the same diameter to enforce the massive flow. What we're going to have in the case of the funnel flow is that we're going to have what we call the dead or non-flowing regions, which are going to hold the material. While at the top, we're going to have the active flow channels, which make the material only running in a funnel shape, but everything on the side is going to be built up or dead.
So other than the mechanical flaws that might prevent like a proper flow, what other factors could contribute to this?
Okay, the cohesion,
Okay.
when you do it for a longer time,
Okay.
because the thing is going to be built up together. Well, as we mentioned, once again, the moisture content, the compressibility. We don't want the thing to be compressed. So we're going to take smaller size, but you don't have to compress something and you're going to find a problem to take it out.
Yeah.
Okay?
So you can't really make the most perfect sandal that would never get.
Nothing perfect in this life.
Yeah. There are
Yes.
factors you can't really control.
Yeah. Usually, if you're going to have the solution for 3 out of 4 is better than nothing. 2 out of 4 better than nothing. Okay?
Yeah.
You try to find a solution for as much as you can
Yeah.
until you are going to have the acceptable design. Yeah. Okay, so how the flow property is going to be determined? First, determined by the experimental. So it should be determined by the testing of the representative sample of the bulk material or materials, and generally tabulated values in codes and handbooks are not adequate. So if you are going to work in a silo or a shipping port or whatever the thing is, you cannot say, okay, well, I checked the tables and they told me that these are the properties. Because if you are storing something in the inland, it's different from next to the sea. It's different from 30 kilometers from the sea. So depending on the humidity you are going to have. Maybe you worked in an area where it started to rain continuously for 3 weeks. So the things has been different. So each time you are going to store something, you have to make a test for it. And actually that's what the people at Wollongong University are doing, because they are next to the harbor. They have a silo, they have the, what they call it, the blue scoop if you want to it in the manufacturing, yeah. They have the coal port and so on. So they have to test everything for those people before they start to do the storage for the material. So flow property testing can be difficult and time consuming and quite expensive. And need to consider a range of the flow property requires for the particular design application. So the flow properties heavily dependent on the sample has been tested. Depending on the particle size distribution, the particle shape, the chemical composition of the particle, the moisture content, the temperature, and is it dangerous to explode it? And it's necessary to remind the flow properties in appropriate testing devices. Now, these are what you asked about. The internal strength, the cohesion, the wall fraction, the time constellation is also going to affect. You are going to have some equations in the assignment number 1, equation number 2, about the time constellation. So even the density of the material is going to be quite different in the second day from the first day from the third day, because it's going to be under pressure, so the density is always going to increase while it's stored in the silo. You are going to have an equation for that, and you have to do some calculation for your solution. So the internal strength, the cohesion, the wall fraction, and the time constellation is going to be used to establish the flow properties or the flowability of the bulk material. And unlike the solid substances, the bulk material capacity to shear and to flow internally without any fundamental failure or alteration of the structure. And unlike the solids, where the bulk material's capacity to support the shear stresses while in static condition. So usually to determine the internal strength, we are going to use the standardized test procedure such as the AS, the Australian standard 3880 for 1991 for the bend flow properties of coal. And actually, this has been almost written by the person who's going to do the lecture for you in week 5, Dr. Peter Whippet from Wollongong University. Yeah, he's number one in his field, and actually he specialized in the pneumatic conveyor, and he was one out of the 10 people who did that back in the 80s. He got his PhD in 1988, and now he's running a project with China because they are number one in material handling at the moment. And I got him in week 5. Hopefully he's going to start with coming because he's usually traveling to China at the same time for 3 months and come back to Australia. He's a nice guy, and you're going to have good experience for the pneumatic conveying. Now, away from that, pneumatic conveying is very important. You may not heard about this one earlier, but actually all the cereal you have on your breakfast has been transported in the factory by using the pneumatic conveyors. Any other conveyor in that is going to smash the particles. Same thing for the pet foods and the other stuff. Okay, so the flow properties, we had to know something called the yield locus concept. So this guy is called Andrew Jinke, which is an American guy who was working on the properties of the bulk materials. So more than 50 years ago, Andrew Jenkins defined the yield locus as means to describe the powder properties. And he developed an approach for the Hobart design, like the massive flow, no arcing, no rat holing. And he introduced the appropriate test method, which is known as the shear test. And this is the experiment actually we're going to do in the lab in week 3. It's not only useful for the mechanical engineer or the storage of the bulk material, but also is very important for the crystallization of the construction material. To understand the yield locus concept, it's helpful to know the relationship between the stress and the strength. How many of you know how to use the Mohr circle? Yeah, I'll give you a refreshment about that. And I'm going to show you a graphical method to get the values of the Mohr circle using the SolidWorks. Okay. So first, let's talk about the stresses. Yes, stress. She's stressed. Yes. Not yet. Okay, so these are an example of the Mohr circles, but we're going to expand that. We have to make 2 circles at the same graph, make some intersection between them to get the properties we would like to have. So this is the case of we are going to have fluid, we are going to put the pressure. Usually in the case of the liquid, we are going to have the shear stress. But in the case of the solids, we are going to have shear stress. So we can make the Mohr circle accordingly. That's considering that the wall is a fraction less, and this is an ideal case. But anyway, where we're going to have the shear stress we're going to occur is going to occur in this plane. So in powder, different stresses can be found in different cutting planes. And even if the material is going to be at rest, the shear stress may occur. So the pairs of values of the normal and the shear stress is acting different in planes from the Mohr stress circle in a normal stresses, shear stresses diagram. And for the liquid, the pressure P is going to be in all direction, and the ratio of the stress for the circle is going to be equal to 0 because distribution in the compressible fluid is going to be different from the solids. So for the Mohr circle cycle, if we're going to take a portion of the material, we're going to have the bulk solid element slide. We can simply calculate the stress alpha, which is going to be the average of the vertical and the horizontal divided by 2, plus the vertical minus the horizontal divided by 2 multiplied by the cosine of the 2 alpha. And the tau value is going to be equal to this vertical stress minus horizontal stress divided by 2 multiplied by the sine of the 2 alpha. Now, I consider that you dislike the equation, so I'm going to try to make it for you as easy as possible. Okay, so once again, I'm going to describe how to do the calculation. Well, actually, get the values by the graphical method, which is going to be more likely for the student to do. Okay, so each point of the Mohr circle is going to represent the stress in one particle cutting plane inclined by the angle alpha. And sigma 1 is the greatest normal stress, which is the major principal stress. And now we are going to go for the strength. So for the unconfined yield stress, strength, for the uniaxial compression test, now you can see we don't have a wall. So we're only going to check about where we're going to have the angle and at what stress. So a hollow cylindrical is going to be filled with fine grained bulk solids. And we're going to have the internal wall of the hollow cylinder assumed to be a fractionless, which is once again an ideal case and is impossible. The bulk solid loaded by the stress is sigma 1, and the consolidation stress is going to be in the vertical direction. Oh, it's time for the break? Yeah, because I want to chat. So you can finish your talk and come back after that. So okay, so go back to your seats. Okay, guys. Okay, guys, go back to your seats. We'll start now.
I want to ask you a question that catches on too after.
Yeah, when we're going to finish. Let's finish the lecture first.
Yeah. Let's get it done.
Hey, guys, we're going to start now. Well, I'm recording that, so it can be used as an evidence against you.
Do the hands on work. Okay? Do hands on work. And then when the board, you just go jump in the computer and do more drawings.
Okay, now let's go to the strength point once again. Okay, so once again, we're going to make the test for the strength of the material we're going to have for testing for the flowability. So we're going to put the material with the finely grained bulk solids in the hollow cylinder. And we're going to assume that the walls are fractionless. And the bulk solid is going to be loaded by a certain stress, delta 1, where with the consolidation stress in the vertical direction. Consolidation means that the stress which is going to compress the material. So the uniform yield strength for the uniaxial compression test, we're going to have the consolidation stress sigma 1, and we're going to check for the measurements of the unconfined yield strength sigma c in the case of the compression strength. With the long-term consolidation, the influence of the time on the strength can be measured, which is going to be called the time consolidation, which is the caking. Now, the time consolidation, it doesn't have to add an extra load on the material. Its own weight is going to cause the compression. Within the time, the things will be compressed down and it's going to build up, and we are going to have something built up like that's what we call the caking. And that's what we had for the example when you leave something for a long time in a jar and you cannot take it out. So the bulk density and the unconfined strength can be simply have a relationship with the bulk density. So the bulk density is an increase with the consolidation stress, sigma 1. The thing is going to start to build up. All the spaces will gone. So definitely the bulk density will be increasing. The flow function is going to also affect it, where the unconfined strength sigma c will increase it with the consolidation stress sigma 1. For the time flow function, same as the flow function, but measured after the long-term consolidation time t, with the sigma 1, which is going to be called the time consolidation for the caking. The question is, where does the flow or the failure is going to be happened and why? So this plane cannot be simply predicted. You have to do the experiment. Maybe you're going to repeat the experiment 10 times. You are going to have 10 different planes to occur for the sliding. So we have the yield limits of the constellated powders, what we call the yield locus. So to check this plane, we can do another test, which called the shear test. It's called the yield shear testing, and that's what we're going to do in the lab. I'm going to show you the machine we're going to use there and give you the principle of it and what the data we can get and what the graph and what the flow property is going to be found. So a yield locus represents the shear stress in which it's going to be required to initiate the flow as a function of the normal stress. A simple word is the yield locus is going to describe strength of the powder material you are testing. And the yield loci is of the cohesive powder is shifted toward the high shear stresses with the increasing of the constellation stresses. So this will be the basic of the experiment we are going to do. As you can see here, we are going to have two halves for the test rig. We are going to add two forces. One of them is going to be the vertical compress the thing down, and the other one try to slide it, which is going to be the Fs. We can check the sigma, which is going to be the normal force divided by the area as we know it, and we can check the tau, which is going to be the sliding force divided by the sliding area. Make the diagram for the tau and the sigma depending on different value for the forces. Then we can sketch these lines. So you can simply see that the increasing of the constellation, as long as we're going to increase the value for the sliding force we're going to have, or the yield loci value. The uniaxial test represented by the stress circles can be done. The yield loci can be found, and we can simply sketch the two more circles to find the value of the sigma v, which is sigma c actually, and the sigma 1. It's going to be the maximum value for each of the circle intersection with the stress bar. So the stress circles represent the stresses at the end of the constellation and at the failure point. The constellation stress sigma 1 is the greatest normal stress acting on the specimen, and it's also known as the major principal stress. To initiate the flow in the silo, actually, the failure creation given by the yield locus must be matched where the shear stresses must be sufficiently large enough to move the particle against each other. And this is the case in the plane represented by the red point, as you can see here. So when you are going to sketch the Mohr circle, the first thing you are going to check is, this is the first Mohr circle. You are going to check the value for the sigma c. And from the center, you are going to go for the contact point with the yield locus line to get what the stress in the failure plane. Then you can find the value of the tau, which is going to be enough to move the particle in the plane. So the shear test we are going to make to check the yield locus is going to represent next. So the yield locus test, we're going to check the shear stress and the bulk density during the shear test operation. That's what we're going to do once again. As I mentioned earlier, we're going to add the normal forces, and we're going to have the sliding forces, and we're going to check the value for the pre-shear and the shear measurements. By taking multiples, we can get the diagrams for the state flow, for the incident flow, and for the last one is going to be for the yield limit or the yield locus value before we can start the Mohr circles. So at the value of the stress pre, then the shear under the normal stress is going to be equal to the shear stress, which is going to be less than the pre-stress. And this has to be repeated for several times, whereby the sigma shear is going to be varied, And thus one obtain the several points, the yield locus can be sketched. We can simply sketch two more circles, as you can see here, 1 and 2. And from the first one, we can find the value of the sigma c. And from this bigger one, we can find the sigma 1. So the left one defining the unconfined yield stress value for the sigma c, while the right one is defining the constellation stress of the sigma 1. The most important parameters in the yield locus for the flow property is finding the constellation stresses sigma 1, the unconfined yield stresses sigma c, the various angles like the phi e, the phi sf, and the phi lin, linear, describing the internal fraction and the YL slope. The bulk density and the flowability then can be found by finding all these values by doing certain calculations. So the flowability factor, the FFC, is the most important for the qualitative applications. To obtain the flow factor or the flowability factor curve of the solid, shear tests are conducted for several constellation load, and then resulting the value of the sigma 1 and the sigma c are going to be plotted in the diagram. For the flow function, if we are going to have the relationship between the unconfined yield pressure and the solid and the constellation pressure is going to look like that. Sigma c is going to be equal to the is going to be a function of the sigma 1. And the flow function, FF, is going to be the change in the sigma 1 divided by the change at the sigma c. Now, according to Jinke, he classified that the solids according to their limiting flow function FF as following. If the value of the flowability is going to be less than 1, that means we're not going to have flowing for the material. If it's going to be more than less than 1, more than less than 2, more than 1, less than 2, we're going to have a very cohesive material. That means it's going to be hardly to flow. If the value is going to be between 4 and 2, we're going to have a cohesive material. If the value is going to be between 10 and 4, we're going to have easy flowing. And if the value of the FF is going to be more than 10, that means we're going to have the free flowing material. So he simply made a graph for that, and according to the yield locus you are going to get, you are going to find simply what will be the intersection, which line. So as you can see here, that as the value of FC, which is the slope of this line, is going to go higher, that means we are going to have free falling. Anything above that, what will be the angle of that? To get the slope of 1, it's 45. Okay, everything above 45 degrees is going to have no flow situation. And in between, easier flow is going to go with the higher value of the slope. So Jinke showed that for a given Hooper, there is an existent critical line such as that as long as the flow function curve is going to be below this line, the strength of the solid is going to be insufficient to support the arc. So if there's no arc, the thing will start to flow. Okay, so the sigma c and the sigma 1 will be no obstruction to the flow. And this critical line was referred as the critical flow factor of the FF of the Hooper, and is the ratio of the critical measure constellation pressure sigma 1 to the critical unconfined pressure sigma c, determined experimentally by knowing that the sigma 1 over sigma c critical is going to be the F1 divided by the FC critical. So as a condition to have the free flow, the sigma 1 over sigma c should be more than the flow factor. The shear test for the wall fraction is going to be simply by determining the wall yield locus instead of the material yield locus, because you know that it's not only the parts going to hold each other, but also the wall's fraction is going to hold the materials from the flow. Now once again, we're going to take a multiple value. We are going to check what will be the wall fraction angle. depending on the stress of the walls against the tau of the wall, the shear stress of the wall. The advantage of the Jinky direct shear tester is only machine that can provide the time constellation data conveniently and cheaply. Always we are going to check the IYL, the TYL, and WYL to be remained in one apparatus. So what's the, it's mentioned here. I was about to ask you what does that mean, but actually it's shown here. All other influences such as the temperature, vibration to be simulated. Okay, so simply this machine can give you the instantaneous slit locus, the time yield locus, and the wall yield locus in one test. So that's almost similar to the machine we are going to use in the lab, but the one they have for the civil engineer is square shape instead of cylindrical shape, but at the end it's going to give you the same results. So for the Jinky shear tester, the first shear tester for the powder and the bulk solids, it was manually operated, requires skill and time, and it's going to take something between 1 to 2 hours for each yield locus. That's the manual one.
Why so long?
Because you have to do it very carefully, and you have to take the measurement. The one we have upstairs is electronic one. So you just put the material, press the button, and it's going to do all the calculation for you. That's why I approximate this is going to take something about 30 minutes to do that.
That's the first test machine that you
Yeah, it's going to be something similar to that.
So it pushes and determines shape.
Yeah. Okay, so that's the standard, the American standard for the Jinky shear cell. And well, actually, I thought about buying one for us, but as long as the civil engineer have one, so we don't have to buy one.
Is the force in constant as force as it determines?
You have to change everything. Well, actually, this one will depend on that, as we mentioned. Okay, yeah, the FS, the shear stress is a function of the FN. Exactly. This one increase this one, the shear stress will be increased. Okay, so as you can see here that the when you are going to add more normal force, you are going to have higher normal stress, and the higher shear force is going to cause what the value of the shear stress you're going to get for the same area, because actually the cross-sectional area is going to be the shear area, is going to be the compression area at the same time. So the cell diameter for the device, actually that's for the one we use in Wollongong University. These dimensions are going to be different. And once again, as I told you, it's going to be a square cross-sectional instead of circular cross-sectional, but it's going to give you the same values. Also, you can do as a ring shear tester. In the ring shear tester, you don't have to slide the things. You're going to flip it, twist it. Yeah, torsional. So applied in powder technology since 1965, and the new design developed in 1992-1993 by Scholz ring shear tester. Displacement volume something between 85 cubic centimeter to 900 cubic centimeters, and for the particle up to a size of 10 millimeter in diameter. Automated test procedure, which can take only 15 minutes per each yield value, and operating time is going to be something about 5 minutes. And the small volume tester can be found also where the value of the 3.5 cubic centimeters up to 70 cubic centimeters. Well, actually, this is fine to get one. This is the automatic ring shear tester. It's a bigger device, and this is once again how the thing is working manually. So you just add in the force 1, force 2, and start to spin the thing. And you're going to have the bottom ring, which is going to be fixed. The other one is going to be dynamic. And we're going to check what will be the forces changing according to the normal force we're going to have. Okay, that's the same thing, actually. Now, the most important thing is what the application of the shear test results. More values, you're going to make more circles. And why we have to do that? For more accuracy, for more uncertainty analysis. Okay, so that's what we have, the mixture type, the concentration we are going to have, the sigma value, the FC value, and what the FF value you are going to have. Now, from your memory, We talked about what the value of the FF and which one is the best and which one is the worst for the flowability. Now the range we had for this material, depending on the pressure we are going to have, we are going to reduce the number. Well, reducing number mean less flow. Okay, that's obvious. More pressure we have here, the sigma, more stress. We are going to compact the material and we're going to start the flowability. The value of the FF something about 2.17. So it's going to be more cohesive at the top. We said that the higher number for the FFC, up to 10 and above, is going to be a free-falling material. So as we are going to reduce the load here to 3,000, well, actually it's just 300 Pascal, it's simply almost double the value of the FFC and made the material going to be more flowable than the actual thing. So actually you're going to get something similar to that, and you have to do the analysis accordingly. And once again, I get to give you an example from the last year lab for the data, and we can spend some time next week on to do the calculation in the class for it. Also, I would like you to start reading the assignment number 1, and we are going to check the question number 1 is going to be the hardest part of it, and we're going to have a discussion about it next week. We'll try to come to here. You bring your understanding to my understanding. I will give you some hints about doing the answer. Then we can spend something about 1 hour try to do something in the class. Now, you know that the submission of all the assignment at the UTN should be electronically because we would like to save the papers. I think that you are going to use the paper anyway. If you are going to do the scanning, if you would like to actually lead the marker to your answer, it's better to type it. But if you cannot type the answer, simply try to write down a very neat handwriting and do a proper scanning. So definitely I will not accept a GPG scanning or GIF or the way the thing is, because many of the students just do it by the phone, and the size is going to be too big, but the resolution is going to be too bad. So actually the scanning and the UTS is free for the student. Just write down everything, put your assignment, cover page, take it to the scanner, scan it, send it to your email, then upload it to the UTS online. Okay, now this is the most important application for the flowability. How we are going to store the thing in the pins or silo or hoopers. Depend on the outlet we are going to have, and that's something we are going to learn next week. The time constellation. Okay, so this is the test for the time constellation, but actually time constellation is happening naturally. We put any material in the barrel, we leave it for a month, we come back, we find out that the things has been constellated and very hard to empty. So its effect occurred when some of the bulk solids continue to gain this strength if it's stored at rest under the compressive stress for a longer time interval from the effect of the adhesive forces between them. Now, this is an example of calculation of the phi t, which is static angle of the internal fraction, using the Mohr circle. So this is the yield locus. And for each one, we are going to make the circle for that. I'll try to search for the video I have for this one. And also, I'll try to search for it now, or maybe I'll try to find it and post it to you, which can give you an answer for the question number 4 for the assignment. So when you come in next week, we can start to do the discussion directly. Okay, so you can see that the value of the FTT is going to be changed with the time. So the FF value, where the time is equal to 0, is going to be different from the 2nd day, the 5th day, and so on. So the thing is start to be more cohesive as the time is going to be increasing. And that's why they don't keep the things in the pins or the silo for a long time. It's better to store it in an open area, for example, for the coal, rather than keep it in silos for a long time. You have the question number 3, I think, which have the equation for the time constellation in the assignments. So simply we can, this is a device to check the wall yield locus for the Jenkins test, direct shear tester. And actually that's the similar to the test device we're going to use. This is the one from Wollongong University. As I told you, the principle is going to say we're only going to add the mass, check the S value, and start to do the diagram and do some calculation using the Excel sheet to give you the equation, and this will give you actually what the value of the flow properties for the material. You have to remember that not all the bulk solids are suitable for the traditional flow property testing. I think we finished with that. Summary practice. Let's check this one. Oh yeah, this is a good example, but this one is not in SI units. So we have test using a shear cell and on the granular materials. The consolidating load was 8 pounds and the cell diameter was 3.75 inches, and estimate the following things. First, what the yield locus we're going to have, what the angle of the internal fraction, what the effective yield locus, and what the effective angle of the internal fraction, what the minor and the major consolidating stresses, the unconfined yield stress, the cohesion, and the value of the flow function of the material. So we started by adding the load of 8 pounds, 6, 4, 5, 3, and 1.5. On the other side, we checked with the device, which found that the shear load was 5, 4.4, 3.5, 2.8, and 1.7. We know what the diameter of the device. So simply, we can find from this one, the sigma, from this one, the tau, by simply divide each value by the area. Now it's up to you. You either can do the calculation totally using the IP, or you can change everything to the SI and do the calculations. But this example is going to remain in the IP values. So that's the normal load, and this is the stress load, and start to do the points on it. Why I can keep it like that? And I'm going to have the same graph. Why? Now I'm using the loads. I'm not using the tau or sigma, because it's the same area, right? So I'm going to make that line, and the contact with the y-axis will simply going to give me the cohesion forces. Okay, so the intersection with the y-axis will give you the value of the cohesion load, which is going to be something about 1.6 here. Now, for this line, using the Excel sheet, I can get the equation for it. Higher R square is going to give you the accuracy of this line. Now, I got the yield locus for this one. I get the cohesion forces for this one. Now, the constellation, the maximum point contact with the x-axis, it's going to be the consolidating load is going to be the 8 pound. Okay, make the intersection between this line from here, the horizontal one, and from the 0, intersect with the consolidating load with the maximum. Okay, I get these two lines. Now, the more circles can be sketched, where again to simply have, this one should be at the 0, by the way. Going to the 0, have the minimum contact, actually something, yeah, minimum contact with the axis, and the other one is going to be in contact with the maximum value, and I can find the value for the maximum values for each circle. Okay, so this is the major consolidating stress, and this is the unconfined yield stress. So I almost got everything I would like to have. I got the yield locus. I got the effective yield locus from this line, which is starting from the 0 point, passing by the maximum consolidating load. And I got the cohesion with this contact. and I sketched the two circles to get the major consolidating stresses and the unconfined yield stresses. So the equation, we said that the FF is equal to the sigma 1 divided by the sigma C, and we can actually find the value of this value by simply dividing the sigma 1 we got from here divided by that, and this will give me the value of the FF. Basically, this will be the first part of the question number 2 in the assignment number 1. The second part is going to be about calculating the diameter of the pin opening. Okay, so next we're going to talk about the bulk material storages. And I think let's take a look to the assignment. And I'll try to send you the video which is going to help you to find the answer for the the Mohr circle part, because it's quite tricky. Okay, where's the Firefox? I promised you to finish by 8:30. We're still 15 minutes to go. Okay, so I will put the recording material here. Either this lecture is going to be uploaded to this folder, and also if I'm going to upload any other videos, for example, the pre-lecture video is going to be in this folder as well. For the assignments, assignment number 1 is open now, it's available for you. Let's have a look for it. Oh, by the way, if you check in the videos on the UTS Online, try to do it with the Chrome, not the Firefox, because in the Firefox it's tried to download the video, and the Chrome is played on the player. Okay, so this will be assignment number 1, and this is question number 1. So in the question number 1, each student is going to have different density, and this will be the only trick we're going to have for this question, because I didn't want to change the other thing. Yeah, okay, so we have a material with a density of 900 plus PQ kilogram per cubic meter. The average hold of time in this silo is going to be for 48 hours before we remove the material. Table number 1 gives you the relevant time consolidating test results from the Jenke shear cell. So what you have to do is sketch the family of the yield Lucey for the results obtained from the experiment using the Mohr circle, and find the following. First, use the Mohr circle to determine the internal angle of the fraction theta, the maximum principal plane stress sigma 1, and the unconfined yield stress sigma c for the yield Lucey. Tabulate the maximum principal plane stress sigma 1 and the unconfined yield stress sigma c for each yield Lucey obtained, and use the data to sketch the flow function, the FMM plot, to determine the CAS value. I'm going to talk about the critical stress value next week. The effective angle of the internal fraction delta can be found graphically by connecting the endpoints of the individual locus by test straight line that passes through the origin, and you can check the slides 111 from the lecture 2. Use Jenke shear cell. Well, actually, this was lecture number 2. It's lecture number 1 in this case. Okay, using the Jenke shear cell to measure the angle of the wall of fraction delta W, and this will something we will learn from next week. So actually what we have here is going to be the following table. And what we get is that for 3 days, for 3 samples, the normal stress and the shear stress. Sample number 2, normal stress, shear stress. Day number 3, normal stress and shear stress. That means you have to sketch 3 yield locus, 6 more circles You have to sigma 1, sigma c for each. At the end, you are going to end up with 6 values. For the wall fraction measurement, it's given here for the normal force and the shear force. And I will show you how to use these values by next week. So just stuck with the values for the, try to do the Mohr circle today. I will try to post the video for you tomorrow, where you can start to do the things and you can simply sketch the Mohr circle using the SolidWorks. Again, to show you a trick, how to move the circle on the Mohr circle sketch to get the value for the C1 and the sigma C and the sigma 1. The question number 2 is going to be about the consolidation for 3 different materials. And once again, the density is going to be different from student to another. And actually, the question number 2 is going to be using the data to calculate the minimum outlet. This should be done next week. The bin design parameter calculated from the study materials next week. Okay, now this one is considered the dimension of the Hubbard geometry, away from the Hubbard geometry, but that's what we have. That's for the flow function and the constellation at the same time. So what you can see here that the density is going to be more within the time because we have the constellation of the material happening in the Hopper. The other question, well, almost all of the questions are related to the lecture number 2. So the first thing we are going to do is just using these data, make the yield locus diagram, try to find the value of the sigma C and sigma 1 for each one, and then we can use it from next week to complete the design procedure for the question number 1. No, it's going to be much better with the SolidWorks, because what's happening with the SolidWorks, when you fix a circle a certain place, when you click on the point, it's going to tell you what the X and the Y value, right? Yeah, I'm going to show you the way how to do it. It's a very simple way. And actually, you know how to use the, the space work at home to use this workspace, yeah, to use the SolidWorks if you don't have it on your own computer. So you don't have to worry about this point anymore.
Can you generate graphs in SolidWorks from your report?
Yeah, you can. You can snapshot or, yeah, take the thing, yeah.
It has multiple Mohr circles on the same one, or is it just a single one?
Well, actually, the more accurate one is to do them separately. Yeah, okay.
But if you want to show all at once, can you do that?
You can, yeah, but you have to choose different color, and this will be the hardest point. Right?
Yeah, so in your assignment, do you want all Mohr circles on different graphs? That's what I'm trying to say.
It's going to be 3 graphs.
3 graphs, yeah.
Each one is going to have 2.
Yeah, that's right.
Okay. So as yeah, you can. Okay. The results are the most important thing, not the